Okay, and I think we're live. Hello, everyone. We're still waiting for a couple panelists, and I hope they will be able to join us very soon. And while we're waiting and while we're getting, hopefully, the YouTube restream going, and that takes a while, we can do a little bit of small talk. So maybe I'll just say something briefly, because we have John Butler here, and he has been amazing in doing the musical pairing of NMA for you guys, and I hope you enjoyed that a lot. And if you have comments for him about, other suggestions, new suggestions, more suggestions, whatever it is, I'm sure he would be more than happy to actually receive those comments. Oh, good morning.
Yeah, I should say,
or good afternoon, or wherever you're in Europe, right? So
yeah, we're in Europe.
Hello.
I'm in Canada. For me, it's good morning.
I should say the music is on Discord as well, so you can get the link to the songs there with the pairing. Juliana, I have this just for you.
Thanks. Where'd you get it from?
Oh, from my Max Planck in Tübingen.
From Tübingen, okay.
Yeah.
It's
probably 10 years old. It's 10 years old. So.
I actually don't have such a mug, so good for you.
Oh, I even have a mouse mat. And I had a cap as well. Oh, when they were closing down, when Heinrich was finishing, I got all the memorabilia I could. That wasn't...
So we should probably get started. Welcome everyone to the Q&A on dynamical systems. Before I introduce the speakers, I would invite everyone to get started in asking your questions. For that, please use the Ask a Question button on the bottom of your screen, and keep the chat for the general discussion. If you want your question to be asked, don't put the question in the chat, put the question in the Ask a Question box, please. And of course, also, as usual, vote on everyone else's questions so that we know which ones you're particularly interested in. And so without further ado, it's my great pleasure to introduce the panelists of today. And I'll start with Juliana Georgieva, who is a professor at the Max Planck Institute for Brain Research and also at the Technical University Munich. And her main sort of interest in research is or revolves around the evolutionary and developmental impacts of, or that evolution and development, the impact that evolution and development has, on brain circuit properties. So welcome, Juliana. Then we have Arvind Kumar. Arvind is at the Stockholm Royal Institute of Technology, and his research, and some of that you have actually sort of seen during the tutorials as well, is on dynamics and information processing in neural networks. And then we have John Butler, who doesn't just do musical pairings for NMA. That's not his job. He does that just for fun, I suppose. Well, you can correct me if I'm wrong. John is at the Trinity College Dublin, and he works on developing essentially dynamical systems tools to understand multisensory processing. So welcome to you all. While all the attendants are asking questions, and again, I encourage you all to do this, maybe I can briefly ask you, panelists, to explain your point of view, your relationship with dynamical systems, or why you think they're particularly cool for your research, and or maybe tell us a little story, fun, sad, whatever, interesting story about dynamical systems. And I apologize in advance for putting you on the spot here. Juliana, would you like to start?
Sure, yes. So I prepared one of the tutorials for the Neuromatch Academy. I believe it's the part that was covered today. So on dynamical systems, and I covered how one could model network dynamics in using dynamical systems. So how can you describe what the network is doing whether it reaches a steady state or it undergoes oscillations, and how does this depend on the properties of the network, for example, the activation curve, interaction of excitation inhibition, strengths of connections, and so on. And I think the work that the students saw in the tutorial kind of nicely illustrates a little bit of the type of research that we do in my group. This was, of course, very introductory, but the types of questions that we ask, where we really use dynamical systems, very nicely fall in this framework. So we study, one of the things we study are networks of neurons, excitatory inhibitory units. In the tutorial, we primarily learn about rate-based units, in particular single excitatory and a single inhibitory population. But in my work, we also study populations of spiking neurons and are interested in how, say, the properties of these spiking neurons, such as whatever firing threshold or ion channel distribution, together with connectivity, structured connectivity or unstructured in terms of probability of connectivity and so on, give rise to interesting network dynamics. And the dynamical systems are a great way to study this, because you can always, the idea is that you can always write the differential equation. So you have a variable that changes in time, in this case, the network activity or the membrane potential of a single neuron. And then you can study effectively the dynamics of the network using this mathematical language of dynamical systems. So you can look for steady states of the dynamics, you can look for these fixed points, you can study their stability. And the other direction, or the other version of dynamical systems that we use, which wasn't discussed in the tutorials, but probably isn't discussed in other tutorials, is synaptic plasticity. So we're really studying how these patterns of activity can shape connectivity, so the strengths of the weights of the connections in the network. And so in this case, we write differential equations not for how the dynamics in the network changes as a function of time, but how the weights change in time. So the equations are not usually dr dt, where r is activity, but dw dt, where w is now the connection strength. But one can really exactly use the same kind of mathematics, the same kind of language. You can look for fixed points by setting dw dt equal to 0, and then once you find the fixed points, you can look at their stability. Yeah, so this is the context in which we use dynamical systems in the group. Basically anything, I mean, there's so many processes in neuroscience that change, whether it's memory potential or weights. As long as you can write the differential equations, you can use the language of dynamical systems to study the properties of these systems. And a funny story, it's a bit hard to tell, but actually I do remember, so one of the courses I took as an undergraduate student, I studied math at Harvey Mudd College in California. So I took first a basic course in dynamical systems, and then I took a more advanced course in dynamical systems. And one of the projects, or one of the exams for the course, was actually a project where we had to read a really, whatever difficult, really mathematical paper in dynamical systems and find a clever way to present it. And I don't remember exactly what even the paper was about, but I just remember that it was about a spider map on a sphere. And because I was in California, one of the props we got from Harvey Mudd, so we just sold the mug from the Max Planck Society, one of the props we got at Harvey Mudd was a beach ball with the Harvey Mudd sign on it. And I remember building a spider out of duct tape to illustrate, and using the beach ball with the Harvey Mudd seal on it to illustrate the spider map. And I know that all of my classmates and my professor found it very interesting and unusual, to the point that, yeah, it became sort of like a little picture that they shared afterwards to new incoming students. I don't know, it's maybe not a funny story for you, but it's a fond memory that I have of my very first course that I took on dynamical systems, and in particular studying the spider map on a sphere based on a spider built out of duct tape. Yeah.
Awesome. Cool. Thank you so much for the little story. Arvind, do you want to say something brief about your research and how it fits with dynamical systems?
Yeah, so whatever Juliana said applies to me as well. So we are interested in function of neuron diversity, and dynamical systems provide us a nice mathematical framework to ask this question. But also, I think besides this, dynamical systems also provide a very nice framework to think of several brain diseases, and to the extent that we can actually call them diseases of dynamics. Doesn't matter how they arise. And some nice classic examples of that will be epilepsy, Parkinson's disease, and so on. So it's a quite powerful framework to think about the brain function as well as dysfunction. Now, a funny story. And since it's a story, I'm pretty sure there are some facts that are wrong and maybe my childish behavior. So one of the first papers I read in neuroscience was from Walter Freeman. Most people perhaps don't even know him. He had recorded EEG from the olfactory bulb of a rabbit. And there, in that paper, he showed nice attractors that were emerging as the animal was exposed to different kinds of stimuli. And that's when I thought, oh, neuroscience is doable. I mean, it's not that far. And I took it a bit too seriously. I get migraine, and one of the symptoms I had is like very bad gasoline smell when I have migraine attack. And it's horrible. And then at some point I thought, oh, look, this is an attractor. And one way to get out of attractor is that I need to give it a very strong random stimulus. So that's what I started doing that time for my migraine aura. And lo and behold, it worked. Now, it's n equal to 1. There's a lot of placebo, so don't take this story seriously, but it's a funny story.
Can I ask, what smell did you use as the perturbation for your internal dynamical system?
So
that was that strong?
So the easiest smell in India that was available is incense that we burned in front of temples.
That's better.
So you
I
just
thought it was
burn
really
in and
bad.
Great. Thank you so much. And I'm very happy to also welcome Karina Kurcho, who managed to join us. Hi, Karina. Thank you for coming in. Karina is at Penn State, and she's interested in interactions between brain connectivity and brain dynamics. It's also very much related to today's topic. So I think this is getting already a little long. So I'll cut the story time short because we have a lot of interesting questions here, and maybe start with the questions already. So the first question is, what's the significance? Oh, that just got voted out. What's the significance of dynamical systems methods in modern neuroscience, especially systems neuroscience? And I think Juliana has already a little bit touched on that, so maybe we can hear from anyone else who would like to take that question.
Well, I'm going to take on it from a slightly different side. Is that dynamical systems kind of pop up because, like, I do a lot of work with EEG, and what you see initially with EEG is oscillations. And so, coming from two sides of the mathematician, the first thing you see is an oscillator, and that's just easily described as a dynamical system. Now, and I had a little touch on this. I wrote some of the materials for the pre-course, and I touched on a paper that they were talking about dynamical systems to describe oscillations. So let's not say dynamical systems are brain. Let's just say mathematics helps us understand experimental data. And if you can understand the mathematics of dynamics of an oscillating system or some kind of funny system, the same kind of rules should apply to the brain. There should be certain rules that should be applied, if you perturb the brain in a certain fashion, as Arvind did by taking the smell, then you should expect the dynamical system should have a similar perturbation. It gets out of a local minimum or a steady state. Actually, on a more clinical level, Parkinson's, I view that, and as Arvind said, it's a dynamical system kind of disease. There's a specific thing I look at called freezing a gait. And what happens is the person starts walking, but they freeze to the ground. And that's very dangerous for them. But how they get themselves out of it, and how I view that is they've somehow reached a stable point in their system, and they'll hit themselves. And they'll get out of the system. So like in a dynamical system, to understand the mathematics of it helps understand the disease of it as well. And so it's the two together are so important. So it's not the methods are vital to understand the brain. And in simple examples like that,
Yeah. Anyone else wants to add an example to this?
Maybe I'll weigh in a little bit.
Please do.
Can you hear me? Okay. Sorry, I had a lot of trouble connecting. I think one of the interesting things from a mathematics perspective, right, is that dynamical systems is really the study of, in some sense, it's really becomes interesting with nonlinear dynamics. So when you take, sort of a differential equations class or something.
Frozen.
So, is Karina frozen just for me or for everyone else too?
Everyone else.
For me as well.
Oh no. Okay. hopefully we will be able to get her back. Let's just continue for now. Okay, would anyone else like to add something to that question about dynamical systems in modern neuroscience?
So I just want to say one thing here, that we shouldn't take the steady states literally. In many ways, these are mathematical idealizations, and if you're looking at the data, not always you will find steady states. In some examples, you will find, for instance, working memory is a great example of that. That a network makes a bifurcation to another fixed point, and that fixed point then corresponds to storage of a memory item. In most cases, I think the way we should think about dynamical systems is that maybe they provide you the baseline state. For instance, you are attentive or not attentive, you are in sleep state or awake state. So this is very important. They give you an operating point around which you can perform your functions.
Cool.
And in diseases, that's what happens. Like these operating points shift. Like in Parkinson, you end up getting oscillatory fixed points, and that just. So.
Yeah.
Sorry, Gunnar.
No, that's perfect.
No, it's one of the questions as well is about that thing. Is like I think there's the models by Xiaojing Wang with the decision-making models, and that forces you into a state. But the problem with those models, and I really love those models, is that then it's very hard for them to get out of the decision. So when the decision is made, and that's not what the brain does, you've made the decision to go left. You don't then for the rest of your life keep saying left. It has to then return back down. So, mathematics are good, but they only describe a certain moment in an event or things like that. And that's why,
this is actually a really good point. Like a lot of these models focus on a particular task at hand, but just get stuck in that task, and then essentially the next iteration of the same task, the next trial, is just you just reinitialize your model randomly, but there's no actual description of the temporal transition from one decision to the next decision, or from one instance of a task to the next instance of a task. And I think this will be really important. Okay,
that's why
Karina back.
That's why I really like Juliana's work that shows the progression of development of the dynamical system. Like playing with the weights is so interesting.
Sorry, Karina, do you want to give it a try again?
Yeah, I could still see all of you guys. It was very strange. I didn't see anything. Yeah, I was just going to emphasize the distinction between linear and nonlinear dynamics. And I think that dynamical systems, like within math, it's really referring mainly to nonlinear dynamics. And this is really, really important for neuroscience. So I would say because fundamentally neural networks are nonlinear in their dynamics. The threshold of the neuron and the saturation and many, many other processes make it nonlinear. And so basically the insights of nonlinear dynamical systems that you can have multiple attractors, that is not just, a single steady state that you go to. Those kinds of ideas, I think, are enormously important for understanding how the brain works. So stop there.
Awesome. Okay, next question is, could you please give an intuition what dynamical systems / brain circuits collapse to steady states means in terms of specific brain functions, for example, memory, etc.? Who would like to give that a go?
I think we already touched up a little bit on this about, the fact that many neural systems, whether it's activity or synaptic weights or any kind of quantity that changes in time that you describe with a differential equation or a system of differential equations, and therefore study basically as a dynamical system, but don't have to have meaningful in terms of neuroscience fixed points, right? So we talked a lot about oscillations, for example, right? So John mentioned oscillations, and I particularly don't study oscillations, but maybe he can comment on this. But having some kind of a limit cycle, right? An oscillation is a very meaningful fixed point, right? This is a steady state that the system gets settled into, right? Any of the rhythms that we see in the brain, the different frequencies, these are all, in some sense, steady states that the system can reach. In terms of memory, for example, so there's quite a bit of description of network dynamics in terms of attractors, right? So you can these can arise in different ways in the networks. Maybe you can structure connectivity in a particular way so that it's not random. Maybe you have, whatever, the emergence of specific clusters, so neurons that are assemblies that are self-connected to each other, right? This is a very natural phenomenon that emerges, for example, through Hebbian plasticity. So in this case, you can have these sort of assemblies that when you look at the activity of such a network that has these self-connected assemblies, this can be reflected, for example, in co-activation of the units that are in that particular assembly. And in the type of work that we do, for example, you can think about this co-activation of these neurons. In other words, you call this an attractor. So it's a dynamical state where the activity gets, basically drawn or sucked into this particular set of neurons being active at the time, is one way in which you can model, for example, a memory, right? So if you maybe during the process of learning or imprinting the non-random connectivity that give rise to these assemblies, this is the process of, say, acquiring the memory, imprinting the memory, and then the actual manifestation, even after you've learned, after you've switched off the process of learning or plasticity, the actual manifestation of activity where you see these neurons co-activate together is effectively an expression of that particular memory that got imprinted through learning. And so the fact that, you have basically fixed points means that you can have these different attractors, these different assemblies be co-active at different times. And so potentially that could mean that these different memories get expressed at different time points in the network.
Cool. Thank you so much. Anyone else wants to provide like an additional information on that? I think Juliana did a great job.
I would just add something very short. I think decision making also can be thought of in this way. So you can think of a decision as, roaming around a little bit in the state space until you settle into an attractor, which then becomes your decision, or then becomes the neural activity that triggers the motor pattern or whatever to implement your decision.
So we talked about sort of like discrete things here in a certain way, right? Decision is a discrete manifestation of something, like a memory is sort of like a discrete thing. What about something continuous, like movement? Do dynamical systems apply there? And
oh, absolutely. It couldn't be more so. I did a lot of work with self-motion and the vestibular system, and so the vestibular system alone is described as a very nice dynamical system. Like most people who study the vestibular system only think in differential equations. They think of it as...
What about steady states in particular?
Well, in relation to steady state, see, if you come from EEG, there is a belief that people are always in steady states and then we kick ourselves out of it. So that's a debate. But the most classic is alpha. That's a steady state of rest, and it disappears when you're not. It appears when you're not attending to something, and disappears when you're not. And then with smaller children, it's delta. Smaller children, like that delta wave we have when we sleep, that's a steady state of sorts. And there's studies looking at that. How can we maintain that stronger? Because all these models disappear. Like in the mathematics, we have them perfect. They get to a state, but in the brain, they'll only last 2 or 3 cycles and then do something strange. So it'd be lovely if we could see these again and again. And there's still such debate, specifically EEG and neurophysiology, about what is entrainment. Do we entrain to a signal, or do we adapt to a signal? And once again, I think dynamical systems are how you can answer those questions in a clearer fashion, if you can model them appropriately. Might sound okay?
Yep. Absolutely. Great.
I mean, I'll be very brief. One could also think about when you study a particular dynamical system to model something, maybe you think of it as like a transient, that the system is at that particular state, in that particular steady state for just a short time during which you model it. Maybe you're modeling a decision or the expression of memory, but ultimately it's really a continuous process, right? So I study development, and you basically have an evolution potentially of multiple steady states through which the system goes as the animal matures. And I think most processes in biology are like that. We never think of a particular, you never reach a steady state and then you're stuck in that steady state for the rest of your life, right? Neuroscience is the whole nervous system is changing all the time as we learn things, as we forget things. And so you're always modeling things at a certain snapshot in time. And so it's really always a continuum.
Yeah, so this is actually good.
Yeah, I wish we had a motor cortex expert, but anyways, I don't know.
I think this is yeah, go ahead.
No, I was going to add one more thing. There's also the concept of the continuous attractor network. Mm-hmm. And so that's a situation where you have an entire line or entire two-dimensional plane of steady states, right? And they're all sort of marginally stable, and they can track the position of an animal in space or of some kind of parametric variable. And so that's a situation where you have a lot of attractors, right? Infinitely many. And you're potentially using changing inputs to move from one to another. And so this is one of the ways that you can sort of hop between steady states is with changing inputs. Even if the network itself stays exactly the same, even if you forget about evolution and development and all that stuff, just changing inputs will change you from one steady state to another. So that's another interesting phenomenon.
Yeah. So these steady state dynamics are often used for modeling movements, and so Juliana brought that up.
And actually, just on the motor, Daniela Bassett just had a paper, I think it was this year. It wasn't describing neuronal behavior, it was describing motor activity, and she used the Lorentz system of equations to see, can you predict? And so, once again, how we move can be described like a complex differential equation. And therefore, and that's a continuous form. Also, decision making, I think, once again, back to the Wang model, which is similar to the Wilson-Cowan. There is an ongoing accumulation of evidence. It is over a shorter time period, but there is a dynamic accumulation of evidence in them as well. So, motor seems more exciting, but decision making, you have to accumulate information. So, there is that part.
Yeah. Okay, I think we should move on to the next question. Vera asks, what is the biological interpretation of some fixed points being unstable compared to stable fixed points? Anyone?
Can I go first? I go first because I actually care a lot about unstable fixed points. Now I'm echoing them. Am I still okay?
You're good.
You're good. Okay. So unstable fixed points. Oh, I'm really echoing. I'm sorry. Unstable fixed points, of course, you never, they're not steady states, right? You don't converge to them. They're not stable equilibria, but they can reflect other kinds of attractors. So usually when you have some kind of a oscillation or a limit cycle, very, very often.
Oh, no.
Oh.
Okay, would anyone
Continue
else
the
like
train of thought of Karina?
Karina, you're frozen again.
Well, I think, yeah, she's frozen again. I think what she was trying to say was that when you have an unstable limit cycle, oftentimes you actually have another stable fixed point somewhere else, so that whatever, what's the word, repelled from something, you're, in reality attracted to something else. But I'm not sure what else she was going to say. I guess, okay, so I don't know, until she comes back, we could talk about what the meaning of stable and unstable fixed points is. Yeah, I mean, I think biologically it just means as we said, if you're talking about network dynamics or memory or decision making, usually if you have a stable fixed point, that means that the dynamics that you're modeling, the temporal process that you're modeling, will eventually converge towards that decision. For example, say you have dynamics that describes the decision-making process, and then you will converge to that. And I think maybe she can continue. I think the important point is also what happens when you have unstable fixed points. Go for it, Karina.
Sorry, I was just going to say, I mean, unstable fixed points, they're unstable because they're not stable in every direction that you would perturb, but they often have a direction that does suck you in near them. And so what can happen, what is very typical for a limit cycle, is that there's an unstable fixed point with some direction sucking you in, and then you kind of spiral out into a limit cycle. And so they can reflect the presence of a more complex attractor. And if you think back on something like the Lorentz attractor, that also has like unstable fixed points associated to it. And so the unstable fixed point, of course, it's not an attractor itself. It's not a stable. It's not a stable steady state, but it can reflect more complex attractors. That's all I wanted to say. I'll stop.
And just on that is that what we think looks very complicated is that we're not plotting it in the right dimensions. So that's why phase plane plots. If you look at, I know you didn't do it, but if you look at the Lorentz system, if you plot everything as a function of time, it looks chaotic. But if you plot things in the phase plane plot, as the students were seeing these last few days, suddenly you see structure because you see how two things are related to each other. So that's why it's so important to think about how your data is represented and how you plot two data against each other. Like that's why getting used to not just think about time, but thinking about how excitation impacts inhibition and plotting them against each other. And similarly, like earlier on in the course as well, when you think of predator-prey, it's the same kind of relationship. You need to have a relationship that looks very dynamic, but actually is very dependent upon each other. And that's why I love phase plane plots so much, is that suddenly something that looks crazy looks beautiful. The Lorentz system is the nicest version of that, though. It always looks like a butterfly. So.
Butterflies.
Yeah.
Also, Arvind, you should say something. I think one of your really important pieces of work is about the propagation of pulse packets through networks. And this is very nicely visualized with stable and unstable dynamics, right? You have a packet and the packet blows up or basically disappears. This is really like one of the landmark papers that we teach in our computer courses. Yeah.
Yeah, that was more a discrete one. So that's why I was keeping quiet,
okay.
because there you are thinking of discrete steps, right? As you go from one layer to another. But I mean, whatever you said makes so much sense. I just want to add one little thing here that more than if you're analyzing brain activity or behavior, I think saddle nodes are perhaps more interesting dynamical fixed points than stable or unstable. That's what you often see. And saddle meaning that there are some stable directions and some unstable directions. And this you can even see in a single neuron. Like you bring it arbitrarily close to the spike threshold and then you wait. And small membrane noise will drive you to spike or not. So you can actually see signatures of those fixed points very easily in the data.
Awesome, thank you. Anyone would like to add something to that? Then we can move to the next question. So the next question is by Emmanuel. Are there tools/libraries to easily model neural population dynamics, in brackets differential equations, on a complex network structure, for example, the functional connectome, etc. And Arvind already put in the as a comment there. Yes, there is of course lots of different tools like Brian and Nest and the virtual brain, etc., etc. Does anyone want to add something to that? I'm not sure to what degree easily model should be addressed here.
So I can add something to it. So Brian and Nest, they are very useful tools to model spiking neural networks of arbitrary complexity. You can put in your favorite neuron model, synapse model, and connection topology. Things like virtual brain, they are more for macroscopic dynamics, like modeling EEG-like signals or fMRI even. And XPP out, this is a kind of a poor man's mathematics, I would say. So it allows you to directly work with differential equations and do symbolic math. That was like before Python had SymPy. And I think if you search for it, you'll find other tools as well. But these three are the most popular ones. There is, of course, Neuron. I shouldn't forget that. Neuron is obviously very, very powerful when it comes to modeling very complicated morphology in the neurons. It also has a way to model networks, but it's not the most efficient. It's only useful for large morphologies. And there is something called MOOS. MOOS is a toolbox which allows you to do multi-scale modeling simultaneously, like chemical cascades in a synapse, then the membrane dynamics and the network dynamics altogether.
So I guess the short answer to the easy part of the question is there's no such thing as easy. Personally, I don't know of a tool that's just plug and play and you sort of question in, answer out, you will have to do some modeling, and easy. It just depends on what you think is easy, essentially. Hopefully, with the tools that you get through NMA, you will find things much easier.
There is one other thing. The SPM, the fMRI one, I think they have built in for dynamic causal modeling differential equations. If you're looking to model MRI or EEG, that's Fristen's. I'd call it a neural mass model, but they call it dynamic causal modeling. And so that's actually inbuilt in that software if you're looking at fMRI data. So that, it of course varies which data you're looking at. And EEG, they have an EEG version as well. So,
yeah. Great, thank you. Okay, next question. Could you give some intuition behind choosing between spiking network model and rate model in a project? Are there cases or research questions for which rate models are particularly useful? That's a great question. I like that. Model choice.
That is a great question. We ask this question all the time in my group. I would say we have a few people in my group who are always, why do we need to model this with spiking networks? Why can we just use rate-based? Honestly, I think the answer to that is just like any question in neuroscience. At what level in computational neuroscience, at what level do you model something, whether it's spiking versus rate-based, or I don't know, anything else you want to ask? It just depends on the type of question that you want to understand. I mean, one sort of cheap answer could be, well, real neurons are spiking, so basically you should always model everything with spiking neurons, because propagation of signals in the brain is really based on these discrete signals, the action potential, so maybe we should always use spikes. But as we know, that's not always the case, because oftentimes if we want to answer a question about that is encoded by rates, or we actually want to understand rate dynamics in a network, then rate-based models and networks are perfectly fine. So I really think it depends. And so then comes, of course, the follow-up question. Okay, so I have a problem that I want to model. So how do I know what I want, what I should do, how I should approach the problem? Then just depends. Think hard about what it is that you care about. So if you care about, if your neurons that you're trying to model have very special adaptive properties, for example, some special refractory period or some firing rate adaptation, so that after you drive them with the current, you know that the firing rate, for example, slows down, then probably it's important to use a spiking model, neuron model, because then you want to capture these dynamics. If you also know that certain types of ion channels play a very important role. For example, you have some channel that gives you very long hyperpolarization, that basically makes your neuron maybe refractory after you've driven it with some current, then maybe it's important to also model this as a spiking neuron. But if what you're trying to capture in your network is how an average populations of excitogen inhibitory neurons behave in time or in response to sort of a current that's provided, a current input that's provided to the entire network, then rate models are perfectly fine and appropriate to model your dynamics. Yeah, in my group we study plasticity, and so again the question is always, okay, is Hebbian rate-based plasticity sufficient, where you can describe the change in the weights just by the product of some function of the pre and the postsynaptic activity in terms of firing rates, or do we actually need to implement some spike-based version of plasticity, for example, STDP of sorts? And again, it depends on what you're trying to answer. If you're trying to describe a phenomenon where you know that the individual timing of the spikes matters, and you know that specific spike motifs matter, then what you need to do is have spiking neurons and implement the spike-based models of plasticity. And equally, if what you're trying to describe is sort of a general change in the connectivity in the network as you, for example, change rates, say you're modeling a scenario in the visual cortex where the rates in the network change, right, when you show different orientations, like what Hubel and Wiesel showed, when neurons orientation tuned and they change their firing rate when you show them different orientations, then it's perfectly fine to use rate-based models and rate-based plasticity.
Anyone would like to add something to that?
Yeah, I'd like to add something. Can you guys still hear me? Am I okay?
Yep. Yeah.
Give me a thumbs down when I.
Oh no.
This was perfect.
I was like, I don't know.
That was a bit quick.
I bet she can't see us.
Yes. I'd actually like to add, to Juliana's is that the question of what model you do or where you model is fundamental as, do you do behavioral research? Do you do EEG research? Do you do fMRI research? All of these type of research questions are answering different facets of the same thing. And so the equations you use are kind of driven by what you like, maybe as well. It seems funny, like people are meant to say science is cold, but like there are certain equations I prefer. So therefore, that's why I spend time with those equations and enjoy those equations more. Because like, for example, what Gina was saying, like, once again, you don't do it, but I'm going to talk about Chao Jingwei. I'll throw the paper in. He had a spiking network paper that was real popular in Neuron. And then a couple of years later, he said, you know what, I've made an equation that has 1,000 differential equations. I could just rewrite that as 2 and I'll get the same answer. Now, it doesn't have the same adaptability, but he was able to show the same thing. So it's a question of what you want to ask. It's a very personal thing as well, but do accept that why some people use an equation is because it's a personal preference. Like the leaky integrating fire is very nice, but I prefer the Ivakovich model for single neurons because it has more excitement in it in my mind. But once again, that's a personal preference. So it's very personal and what question you want to answer. And that was not answering what you were saying. So you can now answer what you were thinking.
Am I back?
Want to give it a try again?
Okay, I'm so sorry. See me now? Yeah?
Yep.
Good? Okay. No, I was going to say a lot of times rate models are nice because they're easier to analyze. So mathematically, I think they're easier to analyze, and even computationally, they may be easier to explore. And so one of the things that I think is a useful strategy is to do both, right? Use a rate model to get an idea of what's going on, but then check if the phenomena that you're seeing holds up in a spiking model. I think that's a good strategy. I'll stop while I'm...
That's very good. I want to start with that, actually. So oftentimes what you will encounter is that you have seen some phenomenon that works very well with rate models, and then you try to replicate it with spiking models, and it will not work. Or the dynamical range within which it works is not the same as in spiking one. So this is a big problem that arises. There are some properties that show up only when you have spikes. If you're like Juliana mentioned about spike timing plasticity, of course, this kind of questions you can't ask. So you have to be very aware, like what is the scope of the model? What kind of problem you're trying to address, and what's the level of explanation? So if you're really trying to explain it in terms of ion channel properties, whether the stability of an attractor or a memory is subject to some ion channels, then obviously you need spiking model. So it's both question as well as the level of explanation you are seeking.
Yeah, and I'll just add, can I just something super quick? I think especially in this issue of trying to capture dynamics of rate-based or phenomenon you see in rate-based networks in spiking networks, this is actually not a trivial issue. And I think some people have thought very hard about this. Like, for example, like Wolfram Gerstner in his recent book, which I think is also available online, has a very nice description of how one can estimate, for example, firing rates in a spiking network. And I'll just say it depends on a lot of things. So usually if you try to do this and you fail, it's, don't be surprised. It depends on the network size. It depends on the type of connectivity that you have in the network, because in the rate-based scenario, what you're really doing is you're just coarse graining, where you're sort of averaging activity over many neurons in time. And what you have to get right is you have to get the right, so you have to have sufficiently large number of neurons, sufficiently correct the bin size over which you want to average to get the rate dynamics right. And these things can really mess up your results. So, in spiking networks, you can get things like finite size effects, where you start seeing things that are not real, but they're there because you have a finite size. And then we can get into arguments, well, isn't the brain also finite, and so on and so forth. But anyway, so there's things like practical things that one needs to consider if you try to match between rate and spike-based things.
Great. So I would like to just add something to that as well, and sort of re-emphasizing what Arvind mostly said. So when we ask, and this is what we're trying to teach you in Neuromatch Academy as well, in particular to the projects, and I do have some echo here too now. So when we're trying to teach you the approach of doing science, it is all based on your question and on your goals. So the way that the particular approach, the particular technique, the particular toolkit that you choose, whether that's a recurrent neural network or a spiking neural network, or rate-based or spiking, or whether your spiking network contains explicit ion channels or not, what detail of the spiking network properties do you want to have in terms of structure, etc., connectivity, etc., etc. This should all be driven by your scientific question and not your personal preferences, ideally. Now, of course, we all are experts in particular fields, so naturally we kind of like, or in particular tools, right? So naturally we like to use them more than other tools. But that's actually often to the detriment of science, because we're not necessarily using the best approach, but rather we choose the one that we're most familiar with, right? And so this is something to keep in mind. I just wanted to re-emphasize that when you do science, please always do start with the question, with your hypotheses, with your goals, make those clear, and then choose the simplest possible model. Always choose the simplest possible model. Make it as complicated as necessary, but keep it as simple as possible. That's sort of a good rule of thumb. And there's no magic formula on how to make this happen. You really just have to think about this yourself for your project.
All your reviewers will force you to.
Sometimes the reviewers will force you. Actually, what I found is that the more you specify your particular goal, your particular question, hypotheses, and the choice of your approach as a function of those, why you choose a particular approach, the more you minimize sort of like the wiggle room that the reviewers have to criticize you on how you approached your question, right? It's very easy if you don't specify anything, you don't explain that, for the reviewer to say like, hey, yeah, but you didn't explain X, but X was totally out of your scope, right? So if I built like, a neural network to look at, properties of single cells or something like that emerge during learning, and then some reviewer comes along like, well, I don't see any Bayesian computations here. And I'm like, whoa, what? I know that Bayesian is the thing, but like, that was not my goal. But if I don't write that out, right, in the communication of my science, then it's very easy to get criticized that way. Okay, and I just wanted to re-emphasize that because it's sort of like one of the most important meta-level scientific things that a lot of people fail, including myself, of course. A lot of people fail at.
Actually, I found sometimes when you get very excited about different methods or different approaches, and you want to include them in the paper, but there's no reason except, look, I did something new. It undermines a paper horrendously. Like the papers I've had the most trouble with are the ones I've done the most work on because I was excited by something that wasn't supremely pertinent for the paper. So like finding or showing a fancy new method isn't as important as answering the question at hand. That's the primary goal of any paper. And I definitely found that early on quite hard to go, but look how much work I did. That's not the premise of the paper. The premise of the paper is, look how I answered my question at hand. And like actually funny, even in my own PhD, the part I might be proudest of is an appendix. Because, sometimes, and I know definitely one of my first papers I wrote, it had a terrible time with the reviewers because in the discussion, I started opening up a whole bag of worms because it wasn't the question at hand. And I'm a big fan of the simplest thing. Like if you can describe a model with just a line, then don't do a differential equation. If you can describe it with a linear differential equation, describe it with a linear differential equation. And if you can't, go to nonlinear. None of these are bad. It's just, I do think people want to show they're smart by showing something's hard as opposed to the answer. I do worry a bit about that sometimes. And it's a personal bugbear of mine of a lot of computational neuroscience papers is people write all these wonderful differential equations. And then in a subsection of a subsection somewhere else, they say, and we solve them using the Runge-Kutta method or the Euler method. And therefore, they're not solving those equations. They're solving the discrete form. So, sometimes I Yeah, because coming from mathematics, in mathematics, you'd always write the explicit algorithm used. You'd always write it out, and that's done less in a lot of comp neuro papers, which means it's hard to reproduce. So
yeah, totally.
Yeah.
That's a whole lot of can of worms, I guess.
Yeah. Sorry, that's a whole other thing.
Okay, we should probably move on to the next question. Yeah. Question is, at this stage, which strategies do you think are best suited for understanding the optimization and the heterogeneity of multisensory processing and awareness, in brackets, such as sound-induced flash illusion, emotional recognition, cross-modal associative learning? Very specific question.
Can I, I'll start into it since that's what I'm big in. I have a couple of answers. There's very little dynamical system description of multisensory integration. And my mind boggles. Multisensory integration is the easiest thing to model on some level because you know what the answer is. Because you have, for example, the beep flash illusion where you hear a beep and you see two flashes. So you think you hear two beeps, how they impact. And this is very important for, well, it has been shown that if people are primed for illusions, they might be more primed for falls in the elderly. And there's a whole literature about this. Now, describing how two areas interact is a big question, and that's weighting. So we were talking earlier about the rate model. Rate models are great, except they are kind of sensitive to changing the weights. So if you suddenly introduce more rates into the rate model, more extra models, it really messes with how you should combine them. So that's, for example, I have not had very great success trying to model multisensory integration using rate models because they're not as adaptable. And that's why neuronal model is better. Describing, so I'm not going to answer fully because then the research agenda for the next 4 years is gone. But I do believe that the simplest approach would be take some of the stuff you're looking at today, like the Wilson-Cowan or these ones, and think about it in a unisensory way. And then think about how you combine them. And there are so many questions in multisensory, like you'll find a paper out today saying that multisensory integration doesn't happen early in the sensory system. And you'll find a paper out tomorrow that says it does. And I think modeling is the best way of trying to do that. There's some lovely work, Jan Drogovitz. He does some nice stuff on some of the visual vestibular data, early on modeling of decision making like that. But once again, not at the neuronal level, at the higher level. So actually, it's a big question in my mind. Maybe I'm completely wrong and I've missed a whole journal of papers, but it's dynamical systems haven't been applied very much to multisensory integration. Maybe the panel will go, "You wrong," and that would make my life a lot easier. But has the panel seen much multisensory integration using dynamical? I don't think so. And I know Dan Goodman, he just tweeted that he has a postdoc coming in to do it. So I best get there ahead of Dan, which seems hard, but because competition is more important than actually working together. I was actually going to email Dan to talk to him.
Yeah, but multisensory integration is often studied using information theory. Yeah,
it is. It is.
There you just go away from this dynamical systems perspective and start treating the brain as an information processing system and have these high-level models.
And actually, Gunnar, the Bayes stuff comes next week, doesn't it?
Sorry?
Yep.
The Bayes part.
Yeah.
Well, next week you're going to see, like, so I have my most popular paper is because I put the word Bayes in it. But a lot of multisensory stuff at the high level is described using Bayesian integration. I'm not going to lie. I put the word Bayesian because one of the reviewers said, "Could you include a prior?" But that kind of high-level stuff, you see a lot of multisensory stuff being described that way. I do not see a lot of low-level single-cell dynamical system modeling of multisensory. So it's a whole. I think it's a very fruitful area. I'm hoping it is. I believe it is.
The key word is mechanistic, no? Like,
yeah.
I guess you're saying if you want to do networks and neurons, like the kind of stuff we're talking about now, that would be like the mechanistic type of modeling. And if you want to do the stuff that Arvin mentioned with information theory, then you probably leave a little bit of the mechanistic implementation aside and you kind of focus more on like integration of information from these different sensory areas, which is totally a correct, fine approach, but it's, again, depends on the question. If you want to gain a mechanistic understanding, then you would use the neurons and networks and probably a dynamical systems approach. And if you just want to focus on how this information gets combined and how much information is propagated downstream, then probably information theory is sufficient. But then you don't gain the mechanistic aspect.
And the work by Mark Ernst and Dora Angelakis is fundamental to our understanding of multisense integration. But once again, that stuff is much higher level. Dora Angelakis stuff does have single cell recordings, but they don't really model that as much. And so there's a lot out there. There's still a lot of work to be done, which is nice. Thankfully.
Tons and tons.
Yeah, tons and tons of work. And actually, that's one thing I used to worry a lot about, was being scooped. But the thing is, there's so much work to be done. And your own interpretation of it matters so much. But yeah. And you'll see this stuff next week, the multisense integration and Bayesian integration.
Absolutely. There's one more question before we wrap it up that I would like to take, because I think it's a really nice and important one. And the question is, what kind of question do dynamical systems answer? They seem to be mostly what models, maybe how models. Can they give insight into the why questions? So this is the how, what, why distinction from Diane and Abbott that we use throughout NMA. Yeah, Arvind, do you want to start with that?
Okay. A beautiful example is Hodgkin-Huxley neuron. And I hope I'm saying a lot of politically incorrect things here. So excuse me for that. So it's a great model, but at the end of the day, it's just a data fitting exercise. They seem to find right differential equation, which they fitted, it worked, it made a beautiful prediction. So it was amazing. However, it does not really explain you why a spike occurs. The real explanation, again, it's my preference, so to say, John will agree, but I think a concise explanation of why a spike occurs came from the Fitsu-Naguma model, where they explained it in the dynamical systems framework. So I think they also give you a very nice why kind of explanations. Dynamics is very inherent, very natural to this system, as we were discussing in the very beginning of this section, session. So I think dynamical systems do provide you why answers as well.
Does anyone want to add something to that? I can add something to that, because so I think any kind of toolkit, and the dynamical systems is a toolkit, right? Essentially can be used in many different ways. So as Arvind said, you can use the Hodgkin-Huxley model to do curve fitting, right? And identify some parameters about neurons or channels or whatever it is. You can also ask, well, why is it that neurons can spike at all? And potentially the answer to that could be, well, because there's ion channels that open and close in a voltage-dependent fashion, right? Different kinds of ion channels. So that would be a why question in that case. And how does the spiking occur? Well, with the exact interplay and timing of the opening and closing and the time constants associated with that, et cetera, et cetera. So in a way, depending on what your question is, depending on how you use this particular toolkit, you can ask different or answer different kinds of questions, right? So it's not that a particular toolkit necessarily is confined to what, how, or why. It depends on how you want to use it. Some toolkits are more powerful. They can ask or answer a wider variety of questions than others. That is true typically, but many toolkits can answer more than one type of questions.
Well, I completely agree. Like it's what you want to use. It's a tool. Like it's, it informs your informs you if you have a question, what tool will you use? Like, so my own self, I've used behavioral, EEG, and modeling, because different parts give you slightly different bit of information about the question you're asking. And I kind of view a lot of computational work, of my own anyway, as an experiment. I would call myself an experimental theorist or something. I don't know. I think of where the running simulations, like, and this is something I think maybe behavioralists don't see and modeling people don't think about, is that like each time you run a model, it's like running an experiment on someone. If you have enough variability, so that it's the thing is the purity of the model. if you have variability in your models, you'll have many different versions of it. So, there should not be a strict distinction between the two. They're just answering questions inside. Why is my data different if I run an experiment in a human, and then I run an experiment in a monkey or a mouse, and then a computational model? And just on a funny thing is, for my whole time, for my first 2 years, I think, when I went into neuroscience, everyone talked about mouse model, and I was going, that's really exciting. They have a mathematical model to describe a mouse. And it only took me 2 years to realize it was a genetic mouse thing, and they didn't have equations. There were a lot of talks I went to where I was really disappointed at the end. Anyway.
Yeah, that's a kind of neuroscience specific jargon.
Oh, it really annoyed me. I was so confused, so confused.
Okay, we're at the end of an hour, so I'd like to thank everyone for being on the panel and sharing your wisdom and knowledge. Is there anything anyone would like to say before we wrap up? Any general advice or anything for the students?
I can pass on an advice I received from Peter Latham. He told me that never simulate until you know what your result will be. And it sounds very circular, but I think it's a very wise thing to do. Juliana mentioned it, that you should have some mathematical framework to do your, let's say, back of the envelope calculations to know what is going on. Otherwise, you have every chance to get lost in the high parameter space, high dimensional space. So the only way out is that you have your expectations right. And this also saves you from a trap often we find ourselves in, that sometimes you get confused whether you are studying the phenomenon you modeled or the model you are using to model the phenomenon. So this dichotomy, I think sooner or later you realize it, but it's good to be aware that this happens.
And I will say one thing that's beautiful. I mean, I think that's super useful advice. The other thing is don't be afraid to go simple. I think ultimately, I've only had my group for 5 years, but now I see it with my students. And certainly when I was a student and a postdoc, I always felt really disappointed when it came to writing the paper. And I always felt like, wow, how can this be a paper? This is so simple. I mean, how could I ever possibly spend a few years on this problem? And it always feels like that in the end of a project. And at the beginning, totally the right place to start is simple. And usually simple leads to more complicated, but importantly leads to insights that really get deep into the problem. And so never start more complicated than you need to. And then when you get to the end, don't think that what you did was too simple.
Just a footnote to that. Leaky integrate fire neuron was developed by Lapik at least 50 years before Hodgkin-Huxley came. So before we understood how spikes occur, Lapik had already compressed it and explained it in a rather simple way. So be brave.
Awesome. Anyone else would like to add something? Karina?
Well, if you can hear me. So my piece of advice that I actually have to repeat to students over and over again is sort of make sure you know, or you're constantly thinking about what is the question that you're asking, right? What is the question that you're trying to answer with whatever you're doing? And especially when you write the paper or write an abstract, like make it clear what is the question.
Absolutely. And always at every single step of the work, go back to the question, because it's so easy to get lost on the way and forget about it. I absolutely agree with that. Thank you.
Also, just about these days, about Neuromatch, students sometimes find suddenly dynamical systems hard. They're not hard. You were just told they were hard. But actually, dynamical systems are quite straightforward, but you have to get used to looking at them. It's just a different thing. Like people said the deep learning section was easy, but that's hard for some people. It's just, you just have to get used to it. You have to understand a bit about parameters. Like the results might be difficult, but the equations themselves actually aren't that hard. And so do give yourself a break. Like on the same thing, I look back now on my PhD, I did a PhD in computational fluid dynamics. And when I finished, I thought I could have done that in 3 months, maybe 2. But on the other hand, I had to learn for 3.5 years how to do it, so that I could do it in 2 months, to do these computations. yeah, do remember that it's very hard to remember when you didn't know stuff. Then suddenly it becomes obvious. And like Juliana said, oh, it could have been so much easier. It's only easy because I actually know the answer now. And that's very, like, don't beat yourself up at the end. That's the worst time to beat yourself up.
I think that's a great final words. So thank you so much, everyone, again, for being on this panel. I think this was very useful. I learned a lot from you guys, so hopefully the students as well. And I'm looking forward to seeing you around the Academy. Take care, everyone.
Thank you, Gunnar. Thank you all. Nice seeing you, Juliana.
Yeah.
Bye.
Bye. Bye, John.
Bye.